Welcome back to the new session on the machine learning course. And today we are going to try to wrap up this discussion about the statistical interpretations of lasso, ridge, and ordinary least squares. And at the same time, we will use this as an opportunity, since we are dealing with the statistical properties of these different methods and relating that to a statistical analysis of the data. We are going to move into the topic of resampling techniques. Resampling techniques, just to give you a brief overview of what that is about. It's a way to better generate expectation values using few data, where you actually use resampling techniques to create a kind of new pseudo data. And one of the techniques is called the bootstrap technique, where you actually reshuffle your data and you pick with replacement new data points. So this is often done in cases where you have a few data. Now, many of the simple cases we've been looking at till now are so-called vanilla data, which means that we can just keep generating as much data as we want. But in a real physical experiment, it's very unlikely that you will be able to generate new data. If you run a nuclear physics experiment at, let's say, Ganil, typically you will run the experiment for a week. And when this week is gone, the data you have is actually the data you have. Alternatively, if you're running a big medical survey where you sample patients for heart disease and you follow these patients for, let's say, 2 or 3 decades, which is not very unlikely, and you sample something like hundreds of thousands of people, then when you are done with the survey, the data you have is the data you have, are the data you have. Data is plural. So if we now look down at the topics which we have, the material which we presented last week, the slides for this session 3 and session 4, these are the slides which we will continue with. And you will find the slide material under this header, which is called Resampling Methods and Bias-Variance Trade-off. So discussing resampling methods leads us also to this bias-variance trade-off, which is a way to analyze the onset of overfitting as a function of the complexity of the model. So when we are fitting a polynomial to a certain data set, what we end up with is a potential for overfitting if we make the polynomial degree too high. So suppose if you have a 5th order polynomial and you try to fit a 20th order polynomial to that data, you may have a perfect training fit, but then when you want to make a prediction on data which were not included in the training process, you may actually fail miserably. And this is an example of overfitting. So this bias-variance trade-off, the way it is presented in the literature and the way it is used in the analysis starts with the mean squared error. That doesn't need to be the cost function, but it starts with the mean squared error as an example, and then you can rewrite the mean squared error in terms of the variance of the model itself and a quantity which we will define, which is called the bias. And these are quantities which will allow us to make an analysis of the model which we have in order to say whether we are overfitting or underfitting. So these are 2 topics which you will encounter again and again in the machine learning literature. So the resampling methods and a way to find out whether you're overfitting or not. And that is often done in terms of this bias-variance trade-off, which has its natural starting point in the mean squared error. Now, we are going to, however, to look today at some basic elements first of the statistical interpretations, and we are going to look at how we can interpret ridge and lasso regression in terms of a statistical analysis. So what I'm going to do now is simply just to dive into the Jupyter notebook, which we started with last week. So there will be some repetition of what we did last week. And then we are going to move over to resampling methods and the bias-variance trade-off. Now, next week, we are going to discuss logistic regression and optimization methods. Then I just wanted to put it, and I'm going to put this in the chat. And the meeting which we are going to have in person, since we are not going to use the weekend of November the 4th and the 5th, then we are going to use the weekend of November the 12th, and this will also be continued on Monday the 13th. So I'm just going to put that in the chat. So the common meeting is for November, so that's a Sunday. So we will just meet in the afternoon, 12th, and Monday the 13th. So we will try to meet them. And the basic idea is that we have then gone through the material and logistic regression, and we have started to discuss optimization so that we can move over to neural networks. And we can then use this time to discuss the first project, which will essentially deal with linear regression and logistic regression, and us implementing these methods. Then we will use the optimization part as a motivation and as an introduction to neural networks. We will also need to use optimizations and numerical derivatives in order to find the optimal parameters for logistic regression, which is a classification problem. So next week, when we now are done with the standard linear regression problems, or what you might call in general, us fitting a continuous function, or just a regression type of problem, we are then going to move into a classification problem. And then logistic regression will be the topic for next week. And then we will need to discuss the calculation of gradients and the optimization part, which has to be solved numerically. Because when we leave ridge and ordinary least squares, we have actually to recur to numerical solutions of the optimization problem. Okay, so I wanted, unless you have any questions, I just wanted to move over to the material this week with a repetition from what we did last week. So let's take a quick look at the Jupyter Notebook from last week. So this is a material both from last week and also for this week here. The video from last week is something you can look up, obviously. And you can also find this video, just to quickly remind you of that. If you go to the README file on the main GitHub address, you will see that there is a link to the videos and also to the handwritten notes which we went through. So you can always look back at the videos from the previous lectures. Okay. So what we were discussing last week was the derivation and interpretations of ridge and lasso regression. And what we are doing now is that we move away from ordinary least squares, which starts with the mean squared error as a definition of the cost function. And then we moved over to two different methods, which use an additional parameter, which is often called a regularization parameter or a shrinkage parameter. And as we demonstrated last week, in particular for ridge regression, this is actually this parameter lambda here, which is larger or equal than 0, is a parameter which reduces the importance of specific components of the parameter beta. And we will see later that this is something which we can interpret in terms of a statistical, we can give it a statistical interpretation using Bayes' theorem. And this is the topic which we will start with today here. And the other method is the so-called lasso regression, which stands for least absolute shrinkage and selection operator. And this is a method where we can actually drive to 0 some of the parameters. In the case of ridge regression, which has a norm 2 squared additional parameter, then in that specific case, it's only in the limit when lambda goes to infinity that we are driving the parameters to 0, as we saw through some demonstrations last week. Now, these methods can, all of them, be used when we have fitted the function, can be used with a mean squared error in order to gauge the quality of the results. So we are not limited by having a cost function given by the least squared error, by the mean squared error, which leads to ordinary least squares, but we can optimize a different function which now contains this parameter lambda. Now, we did not care about the constraint on the beta values, and this is the standard first order implementation of ridge and lasso regression, but we could have actually put a constraint on it, and that would lead to a convex optimization problem with constraints, which is something we will discuss a little bit later when we introduce a method which is called support vector machines. Now, deriving the ridge regression gave us this expression for the optimal parameters, and this is to be compared with the ordinary least squares. So originally, the ridge method was introduced by simply adding a parameter lambda to the diagonal matrix elements, and that would cure the problem of determinants which would be 0 for this matrix, or that the matrix is singular, having at least one eigenvalue which is 0, or determinant which is 0. And in case of singularities, we could remove the singularities by a cheap ad hoc trick by simply adding a small constant lambda. However, if we now look at what we've done here, where we have included a totally different cost function, we are now optimizing a different problem with respect to the mean squared error. And we have an optimization problem here where we now end up with a problem to invert, which can always be inverted because this x transpose times x, as we discussed last week, can have some eigenvalues which are 0. However, when we add this lambda, when lambda being a parameter larger than 0, this will always be a matrix which can be inverted. So we went through this singular value decomposition analysis, and we showed that the ordinary least squares can be written out like this, except that now the sum runs up only to the number of features which we have, which means that we're actually projecting out a specific set of features of the original data set Y, and where we are using the orthogonal vectors defined by this orthogonal matrix U. So every column of this matrix U defines an orthogonal vector. And these are the vectors which are written with lowercase letters here. And you can see now that in the case when we have a simpler example, where we simply assume that this x transpose times x is given by a identity matrix, which means that the design matrix itself is orthonormal, then we can give a simple interpretation of ridge regression in terms of ordinary least squares, where we actually have a 1 plus 1 over lambda parameter. So all the parameters beta get shrinked by this lambda here, and lambda is always larger than or equal to 0. So when we do the lasso method, then we have to take into account the fact that we have a sign here. And in many, many applications, people would actually, since we have a discontinuity at 0, many people actually put that value to 0. That's in a way, it's a little bit cheating, but this is a way by which it is done numerically often. And in this specific case, we actually have to solve a convex optimization problem where we have a constraint in terms of the sign over the parameters lambda. So which means that we have to implement these two options depending on the value of lambda. And in this specific case, what we end up with is actually a problem which we have to solve numerically anyway. So it's only in the case of ordinary least squares and ridge regression where we can actually do that. We went through some examples, and I'm going to skip them because these were examples which were meant to illustrate ridge and lasso regression. So I will skip these and not rerun them, and then move to the statistical interpretations which we dealt with last week. And one of the things which we went through was a reminder of the model which we have made for the data. So keep in mind now that there is a basic assumption, and you can think of that as a model for the data. But on the other hand, you could also think of that as an assumption about the data. So the assumption we are making is that in the case of a continuous function y, there is a continuous function f, which is assumed to be a non-deterministic or non-stochastic function. So this is a well-defined function. It could be a function of cosines, of sines, or any other type of polynomial. And then, sorry for this. And then there is a noise, which we assume to be normally distributed. Now, the problem with which we have is obviously that we don't know the function f, and then we approximate f with the y tilde, which is our model. So this is where we define the model, although you could say that by making this assumption, you could think of that as a model for the data itself. So there are two levels of modeling here. Now, the function y tilde is assumed to be given by the design matrix times a linear dependence in terms of this beta, and that's the name linear regression. So we're assuming that there is a linear dependence in the unknown parameter. And one of the things we showed last week is that we could then rewrite the expectation value of this quantity here, since epsilon I is given by a normal distribution with mean 0. Then we would have so this is a sum over the parameters j or beta, all the parameters. So this is the row I in the matrix X multiplied with the column vectors beta. And then we could also define the variance to be equal to sigma squared. And we can repeat the same thing with the parameters beta. And we find that the expectation value of the parameter beta is equal to beta. And we normally say that the estimator or the optimal parameters are unbiased. And we could also find that the variance is given by this variance of the noise, which we have, times the inverse of the design matrix transposed times the design matrix. And if we use ridge regression, it's also pretty easy to find that this quantity here simply has to be given by this matrix, which has to be inverted. And in general, the variance for ridge regression for the parameters beta is different from the variance from ordinary least squares. And we can also compute the variance for the parameters beta, and we can actually show that the variance for ordinary least squares is often larger than is larger than the variance for the ridge parameters. Now, the next thing which we did last time was to derive ordinary least squares from a probability distribution. And this is where we essentially ended last week. So one of the assumptions we have made now is that the x's, which enter the design matrix, are non-stochastic variables. And the only stochasticity comes in the noise term, which we assume to be given by a normal distribution, and with a zero mean value, and then an undetermined variance. So what we can then do with the expectation value we have here, and the variance for y, so the variance for y is given by the same as the noise has, except that now it has a mean value, which is given by this design matrix rho multiplied with a vector beta. So remember now that this is just a rho which has been multiplied with the vector beta, so this becomes a scalar. And then we can use a normal distribution for the, since we assume that the noise is normally distributed, then we can make an assumption about the data so that the data is also, the output is also normally distributed. Whereas X is not affected by these distributions. It's a non-stochastic variable, which does not depend on this distribution here. And then what we could do, and what we did last time, was then to simply rewrite this probability like this. So it's normalized with 2 pi sigma squared. And we assume that these events are independent and identically distributed. And you will see this acronym IID. And then we can rewrite the probability in terms of this. And so we have the product of the probability. Since these are independent, every y of I is independent of the other y of j. And then, since they have the same probability distribution, we can then make an ansatz for the total probability, which now depends or is given by the product of the different probabilities. And we wrote this in a more compact way, where D is now the domain of the events which we have, and where the events are given by a non-stochastic variable x and a stochastic variable y. And then what we used then was what's normally called a maximum likelihood estimation. So we find the parameter beta by maximizing this function. So we want to find a beta which maximizes the probability. We don't want to find a beta which minimizes the probability. So that sounds pretty obvious. And what we did then was, since it's more cumbersome to maximize a product than to maximize the log or minimize the negative log, and the log is either a concave, or if we have a negative sign, it's a convex function. And then we could simply take the derivative of the cost function in terms of, oops, there is a parenthesis missing here. So we take our cost function is now the log of the probabilities. So that means that we just get a sum. And when we take the sum, we simply end up with this equation here. Now, the first term, which you have here, is a constant. Sigma squared is a constant, which is undetermined. We can multiply it away when we require it to be 0. And then we get the same equations as we had in ordinary least squares. So this is the way we can now link the ordinary least squares with a statistical interpretation. So the statistical interpretation is that the quantities y are given by a normal distribution with a specific mean value and a specific variance. And then the total probability, which now takes into account all the possible events, is simply the product of all these events. So this is what was derived back in the 1850s. So we are talking about something which is getting close to 200 years. And one of the reasons why we include ordinary least squares and some of these simpler methods in a typical machine learning course is that we have simpler statistical interpretations. We have the possibility to calculate some expectation values analytically. And we can build in many of the basic concepts in machine learning. So when we come to neural networks and deep learning, which is more difficult to obtain, or it's actually basically impossible to obtain analytical expressions, then we have built up some kind of insight and understanding of what goes on in the statistical training of a given model. So what I wanted to say something about now is a quick reminder of statistics and Bayes' theorem. And we are going to use Bayes' theorem to give a statistical interpretation of ridge and lasso regression. And when we are done with that, we will move over to the resampling methods and the bias-variance trade-off, which is a kind of litmus test for all the models which we're dealing with, in particular if we're dealing with regression. So I just wanted to give you a quick reminder of some important theorems in statistics. And I'm just going to state them. And Bayes' theorem is actually very easy to derive if we look back at some of the basic axioms from statistics. So we have a set of events, so with x and y, and we can define the likelihood for x and y as p of x and p of y. So these do not need to now to be the inputs and the outputs in our models. So these could just be some stochastic variables. And they are governed by some specific probability distribution here. And then we would typically write the likelihood of a specific event as P of X equal to X of I, or just P of I with a subscript I here. And then we have the union of events, which is now given by P of X plus P of Y minus P of X not being member of X and Y. And then we have something which is called the joint probability, which is now given as the product of X and Y with a given constraint. So what we have is the probability of P of Y, which you see here, multiplied with the probability of X with given Y. Alternatively, you can write it like this. And these are some of the basic statements which you will find in the beginning of a textbook or a course on statistics. So when you look at this quantity here with P of X with this vertical bar here and Y, this is read as the likelihood of obtaining X given Y. If these are independent events, so that means we are thinking of perhaps independent and identically distributed variables with the same probability distribution, like the case with the Y's given by a product of Gaussians, then we would simply write it out like this. That's the case if we have independent events. If not, we would have to stay with this product rule, which you have here. Now, there's something which is called the marginal probability. So that means that what we are doing then is that we are simply summing up over one of the variables. And this leads often to us getting rid of one of the degrees of freedom. And this is something which is important when we are looking at, let's say, some normalization properties or probabilities. So the marginal probability, if it depends on more than just one variable, is now given by us summing away one or many of the other variables so that we're just left with P of X. So we would sum over all the events Y here. And this is normally written like probability of X with a given Y. And then we are simply summing away them. And then we have something which is called the conditional probability. So if this P of Y is larger than 0, that's also important. We can actually use what you have here. So this is the probability of X and Y. And then we would simply now use the conditional probability and the marginal with the marginal probability and the product rule. And then we can define the conditional probability of X and Y, X given Y, which is now given in terms of these two terms here. And if we combine the conditional probability with the marginal probability and the product rule, we obtain Bayes' theorem, which now is given in terms of the likelihood of X given Y, which is now multiplied by Y, the likelihood of Y given X, times the probability of X, divided by a marginal probability, which is a normalization constant. Now, this acts as a normalization constant. So this quantity which you see here is the posterior probability. This quantity which you see here is called the likelihood, and this P of X is called the prior. So both of these quantities here, they depend on a specific assumption we make about the data. So the in case this P of X here is given by uniform distribution and P of Y is given by a Gaussian, then the resulting probability is also Gaussian multiplied by a constant given by the normalization factor you have here and this uniform distribution, P of X. So the way you can view this is that like the quantity on the right-hand side of the theorem is evaluated for the observed data and can be viewed as a function of the parameter space represented by X. And this function is not necessarily normalized and is normally called the likelihood function. The function P of X is called the prior, while the function on the left-hand side is called the posterior probability. And Bayesian statistic is widely used in analysis of data. And when we, as physicists, are using machine learning and these statistical methods, what we often want is both the possibility to make predictions with a fit to the data, like we've been doing with linear regression. We want to find correlations in the data, but we also want to estimate the errors on the parameters which we develop, which means that we would definitely like to have a probability distribution which governs our data. And when we have that, we can also estimate the variance and standard deviations, which then give us an error on the either the outputs which we're looking at or on the specific parameters. So I just wanted to give you a quick example if you're not too familiar with the application of Bayes' theorem. So just to give you a kind of feeling of what it is about, because we are going to use that to interpret lasso and ridge regression. So if you think of a simple example of using Bayes' theorem, you could think of an example where you're looking at mammography. And these scans are often used to rule out possible breast cancer cases. So you could say that we could define the sensitivity for a positive event by a given variable x. And this takes binary values with x equal 1 representing a positive event and x equals 0 being a negative event. And we reserve y as a classification parameter for either negative or a positive breast cancer confirmation. So in the examples I'm using here, well, I should actually have inverted the wordings, but positive means that you have breast cancer, and although none of us would actually consider that as being a positive thing. But in this case, we are just using one as saying that there is a positive hit, which means that the patient has actually breast cancer. So we are letting y equal 1 represent the case of having breast cancer, and y equals 0 as not. So let us now assume that if you have breast cancer, the test will be positive with a probability of 0.8. So that means that x equal 1, so your mammography gives a positive hit. And so you have the probability of x equal 1 given y equal 1, which is 0.8. That sounds scary because it sounds that there is a likelihood of 80% for having cancer. This is, however, not correct. And you will see that from the Bayesian analysis which follows. So doing it correctly means the following. If you look at national data on breast cancer, the general likelihood of developing breast cancer is a very small number. And if you scan many populations, you will often see that this is a probability which is very small. And in this case, it's 10 to the minus on the order of the, so you have, this is 0.04%, so it's a very low percentage. So what we are going to do now is to use Bayes' theorem to actually estimate what is the probability of having breast cancer given that the mammography gives a positive hit. So we need then to use Bayes' theorem in the sense that we have x equal to 1 and y of I equal to 1 multiplied with y of I equal to 1, which is this number 0.04. So we have now said that this is given by 0.8 here. So in the numerator, we have 0.8 times 0.04. And then we have to divide it by this marginal probability, which is a normalization constant. So the probability in case there is a positive hit in the from the mammography and resulting in the patient having breast cancer, this probability is much smaller. It's a 3% chance of having breast cancer and not 80% as you see here. So these are this is the way you would actually use these quantities of the likelihood of a prior and the final posterior probability, because the question we have to ask is not this one. So this one simply says the probability that the mammography will result in a positive test, given that you have breast cancer. But what we want to ask is actually, what is the probability of having breast cancer in case the mammography gives a positive hit? So that's the probability which we actually, the question which we have to ask. And that probability is much, much smaller. So when we now move back to Bayes' theorem and ridge and lasso regression, so I'm going to use the slides for the rest of the lecture here. And because this is something which you can think more as a kind of background information. We are not going to use this in actual calculations, but it's useful to have a feeling of what this is. Because when you take a course on machine learning, or you go into any textbook, you will see these kind of statistical interpretations being used again and again. And as I said, in the beginning of the semester, when we look at machine learning, we will be less interested in a probabilistic interpretation. We are not going to use that very much, but we will try to fit the data with some kind of model. But keep in mind that there is an underlying statistical interpretation of what we are doing. So I just wanted to give you this kind of background information here. So if we look at the, let us just go down here. When we now look at the Bayes' theorem, we can actually gain a better intuition about ridge and lasso regression. So when we did ordinary least squares, what we assume then is that the data, the output data, the y's which we have here, are now governed by a Gaussian distribution where we have a specific mean value and a specific variance. So this is an assumption we made. So what we found was actually the probability of the given output with a given beta parameter. And then we optimize this. Now, what we can do now is to ask ourselves, what is the probability of these parameters beta with a given input here and output? So that means that we can use Bayes' theorem, where we use the result you see here and multiply that with a prior for the parameters beta. So that means that we can now make a model for the parameter beta. So we already have a model for the likelihood if we use Bayes' theorem, but then we need to make an ansatz for the parameters beta. And by choosing specific probabilities, so in the standard ordinary least squares, we assume that the betas are given by a uniform distribution. So that means that every beta is equally likely. So what we could do now is, on the other hand, to simply assume that the parameters beta follow a Gaussian with a mean value 0 and a given variance. So this is a model which we make, and keep in mind that when we deal with Bayesian statistics, we are always making up a model. So you have a prior and you have a belief in this specific prior. So there is nothing given, or how to say, magical about this prior, except that we just make a model for it. And this obviously leads to a model dependence when you deal with Bayesian statistics. Now, if we do that, then our total probability is simply going to be given by the Gaussian we had here for the so-called likelihood function, which we have from ordinary least squares, multiplied with a probability distribution or a prior for the parameters beta. And then we can ask ourselves, what are the optimal parameters beta, which maximize this probability or minimize the log of this probability? So if we do that, if we now take the derivatives of this function as we did before with ordinary least squares, we actually end up with a cost function when we take the inverse log of this quantity here and leave out this parameter which you see here. So we take minus log of this quantity multiplied with that quantity. So we just end up with the two given terms here. Now, if you then look at this parameter lambda, which we had when we introduced the ridge regression, what we simply have then is that we can interpret this lambda parameter as the variance in the parameter beta. So making lambda huge means that we are making a variance of the parameter beta very small. This has interesting interpretations when we are looking at the values of the beta parameters when we have a large variance in these parameters. Because if there is a large variance here in the parameters beta, if they vary a lot, we can then actually use this lambda here as a tuning parameter to get rid of parameters beta which have a large variance. So the way we interpret this now is that if we have a very, very small variance, that corresponds to a large value of lambda. If we have a very, very large parameter, a very large variance of the parameter, that corresponds to a lambda which becomes small. So when we tune lambda, it means that in ridge regression and also in lasso regression, we can actually tune the variance of the parameters beta. So this is the link with statistics and lasso ridge regression. And then we can use the same for lasso. And in that case, if we use something which is called the Laplace distribution, that's an exponential. So instead of having a Gaussian for the parameters beta, which is centered with mean value 0, and a specific variance, tau squared, we can now simply use an exponential distribution, which in our case, since it has an absolute value, is given by a Laplace distribution. And if we do that, and now take the minus log of these terms here, we end up with this term here, which is nothing but the optimization of lasso regression with a parameter lambda, where lambda is now given by 1 over tau. And this tau here is again the variance of this exponential or Laplace distribution. So we have a nice statistical interpretation of lasso and ridge regression in terms of Bayes' theorem, where the basic assumption now is that we use Bayes' theorem, and we've been a little bit sloppy here. We don't care about the normalization constant. There is a normalization constant we have to keep in mind. But when we take minus log of this quantity and the derivative, this normalization constant disappears. So we are simply left with a probability distribution given by a prior here, multiplied with the likelihood, and then we can simply set, besides the normalization constant, as you can see here, omitting the normalization factor, we end up with the standard expression which we have seen before. And then we take the derivative of this quantity and find the same equations which we did for ridge regression. And similarly, when we do lasso regression, the way we interpret this, these parameters lambda, is that these parameters lambda can be interpreted as the inverse variance of a given exponential. In this case, it's an exponential distribution, a Laplace distribution, or the standard Gaussian distribution, or in our case, this would be the normal distribution. So this is the kind of statistical interpretation we can make of ridge and lasso regression. So after this, we are now going, after the break, we are going to look at resampling techniques. And then we are going also to derive what is called the bias-variance tradeoff. So this was the kind of statistical digression, which we are not going to use that much, but it can be useful in order to understand a lasso and a ridge versus an ordinary least squares fitting. Okay, so I'm going to stop here before we move into the next topic, which is going to be more useful for us, and that's about the bias-variance trade-off and resampling techniques. So the topic which we are going to spend some time on, and which is also a topic which is something we need to include when we analyze a given method, whether this is a classification problem or a fitting a function problem, like a regression problem we've been discussing till now. So one of the reasons why we deal with resampling techniques, and there are two widely used ones. One is called cross-validation, and the other one is called the bootstrap. And some of you may have met these techniques already. You may encounter other ones, like the jackknife method, which was a precursor to the bootstrap method. And there's also a method which is called the blocking method. So all these methods, they try in a way or the other one to get a better estimate of expectation values, given a limited data set. So let me try to explain what this means by switching over to the whiteboard and look at some specific examples. Now, what I wanted also to say a little bit about is when we look at the statistical data analysis, the way we can treat the simulations which we are running, they have to be treated in a way as numerical experiments. So when we are now running some of these regression cases where we are fitting a polynomial, we can then, since we run the calculations or the analysis as a kind of numerical experiment, we can use many of the same tools which we use in statistics when we analyze experimental data. This applies in particular to the kind of simpler cases we have now, but else we do actually have experimental data which we need to analyze. So the same tools are normally then used both in numerical experiments when we just have some vanilla test set, which we are going to discuss a little bit later, or when we now want, as in all experiments, we are actually looking at expectation values and we want to estimate how accurate they are. So we would like to have a reliable estimate of an expectation value, and we would also like to have a reliable estimate of, let's say, the standard deviation. So when we are computing the mean squared error, what we want to then is to be sure that the mean squared error we present is a quantity we think is the best we could get. And the best we could get with the limited data set which we have. And as in experiments, in general, we have typically two classes of errors, statistical errors and systematical errors. Now, the systematical errors are much, much more difficult to model, whereas statistical errors can actually be dealt with the standard tools from statistics. And this is actually what we are going to discuss when it comes to resampling methods. So one of the things which we are going to look at first is just a simple example where we now focus on the mean squared error. And we are going to split the data into test and training data. And then we can discuss the prediction error, or simply the test error, and where we have a fixed training set and a fixed test error set. And we can then predict the training error, which is the average loss over the training data. So let's take a look at these things by diving into the whiteboard here. So let's take away the slides and just move over to the whiteboard and slow down the pace a little bit. So if we now look at a typical example, which we end up with, so we have defined some kind of test function, cost function. So we have defined a cost function, which is typically a sum, so of the parameters beta and the data set which we have. So we are running from 0 to n-1. These are the data we have. And there is a function L. And this function may depend on y of I, of x of I, and these parameters beta. So if we looked at the mean squared error, this was given by 1 over n, and we have a sum from I equals 0 to n-1. And then we had the y of I minus y of I tilde, which is our model squared. And this is something which we would rewrite as 1 over n from I equals 0 to n-1. And since we're dealing with linear regression, this is given by a sum over j equals 0 to the number of features which we have. So this is a P. And this contains xij, the design matrix elements. And then we have the unknown quantity beta, which we want to optimize. So this is a typical example of a cost function which we have been using, where this L is now given by the individual contribution. That's often called the loss function. But then these names are used interchangeably. So sometimes one calls the cost function just for the loss function. So the quantity which you see here, if we now look at the mean squared error, we can actually rewrite that as an expectation value. And if we use this vector notation as we had before, we would now have this as given by y minus this x, the design matrix, and then we have the norm 2 squared. And keep in mind now that when we define an expectation value, suppose now we are taking a moment of a parameter x of n. This is in principle given by the domain where x is defined. And then we have x to the power of n. And if we know the probability distribution, p of x, then we can calculate this quantity. But normally, this is unknown. And what we are left with is actually the sample mean value. So this would now, if we look at the mean value, which is the expectation value of x, this is given by x d. Sorry, let me just rewrite this one because it came a little bit x element in d, and then we have x of p of x of d of x. This is the quantity which we ideally would like to calculate, but we don't know p of x. So what we have is actually the sample mean, so which I'm going to label like this mu of x, which is 1 divided by n, and it has a sum over all the observations which we make. And this quantity here is what we call the sample mean. So when we look at the mean squared error, that is also sample mean. So this is a sample mean squared error. Now, ideally, we would like to calculate the mean squared error with a probability distribution, but we cannot do that. And these quantities which we calculate, then the sample observables, they are not necessarily equal to the true observable. So with a limited data set, what we want now is to use resampling techniques to be able to make a better assessment of these mean values. Now, let's now look at a case which illustrates what may happen when we deal with different mean squared errors and a set of data which we are training. So we could now run, so we could calculate the training mean squared error and test mean squared error with different data sets. Different, but limited. So we don't have an infinity of data. And that's actually the problem which we typically end up with. Just to give you an example, when I run some Monte Carlo simulations of quantum mechanical observables, then these are calculations which can take weeks. And I would end up with some few outputs, which could be something like 100 to 200. And based on these results, I would like to calculate some expectation values, some mean values, and some variances. And that's where resampling techniques come in as a cheap way to generate new data. So, but limited. So suppose now that we make these calculations here, and we plot the mean squared error for training and for test. as a function of the complexity of the model. And the simplest kind of complexity we can think of is just a given polynomial order. So the blue lines, which you're going to see here, they are going to represent the results from the training data. So we have the complexity of the model here. So I could now get a result which looks like this with one data set. So let's just call this MSE train T1. So I generate randomly a data set. And then I split this data set in train and test. And then I compute the mean squared error. Suppose I generate 1,000 points randomly. And then I get the mean squared error for training. And this reaches at a certain point. And for those of you who have done the exercises, you may have seen a behavior which goes like this. So this would be the mean squared error. And this is test. So the so the red curves are test data, which we have left out of the training. And the blue lines are the train data. Now, what I'm going to do now is, one is to repeat this generation of data points. So I'm going to produce new 1,000 points, and then I'm going to train a new model. So if I train a new model, what could happen now, and I split it in train and test again, I would get something which perhaps looks like this. Now, for the training case, when we increase the complexity of the model, this will be train 2. And then I could get something which goes like this. So we don't know a priori where it ends. So it could look something like this. So this could be MSE T2. In general, what I could get is a kind of region here where I have my mean squared error test, and the values may vary within a specific band here. So let's just make a band like this. But all the models tend to give some kind of minimum around here where we would have the optimal model. Because beyond that point, we are starting to overfit. So the mean squared error goes up. So this is optimal model. And then for the training model, we could see perhaps a similar thing, but often the training model becomes a little bit more narrow. But still, depending on the data set, and if we have few data, everything which you see here will depend on the amount of data. So all results here depend on amount of data. So if I rerun this with, instead of 1,000 points, and if I rerun this with 100, the behavior will look differently. Everything we do is limited by the number of data which we have. Keep that in mind. That's the important thing here. And that's why we use resampling techniques, because what we want now is to make an estimate of the mean squared error. So perhaps the mean squared error is this one, MSE for test. And then there is a value here, which is the average of all these experiments which we've been running. So this could be the blue line is the final train MSE. So that means that what we are doing now is that the total MSE is going to be given by an expectation value. So the MSE train is now going to be given by 1 over B, where B is all the number of samples which we are doing now. And this runs over I equal 1 up to the final value B. And then I have the MSE train. And with a subscript I here. So we take the average of all the mean squared errors. Then we would do the same with the test. So we have performed a given number of experiments. And if we are using some simple functions like a polynomial, which we are fitting, to refit this function many, many times with different data sets is something which we can easily run. So we would have an MSE test then for case I. So the quantities which you now see, so this will be the red one. So our mean squared errors are now going to be given by these kind of averages over all the expectation values which we've been calculating with the different models. So you could think of us getting a kind of band of results, where one thing we observe is that the mean squared error for training is an error which becomes smaller and smaller because we are simply using all the points to really fit an optimal model. And as we increase the complexity, we can let all the points be fitted to perfection. But when we fit a model to perfection, what happens then is that when we test it or we use it on some data which was not included in the training, we may actually fail. And that leads to a typical case of overfitting. And you will see that reflected in the fact that the mean squared error of the data which were not included in the training will typically be worse than the training model. And you will see a typical behavior which runs like what you see here. Now, again, these results will depend on the amount of data. If you have lots of data, this kind of bend up of the mean squared error for training will take place at a later stage. And depending on the complexity of the model, you may see this bend up or not. Any questions so far? Okay, so what we are going to do now is to use resampling techniques to generate new data. So keep in mind now that everything I said till now is based on us being able to just regenerate new data. This is something which is simple when you have some vanilla data like those which we have for the fitting of these polynomials with a simple function. However, if we have real data, as I mentioned in the beginning of the previous lecture, if we have real data, it's very unlikely that you will be allowed to rerun the experiment. If you run a nuclear physics experiment or particle physics experiment, which runs over days and weeks, the price tag for a simple experiment is actually in the millions of euros, which means that unless you have a case for a coming Nobel Prize, it's very unlikely that the Physics Advisory Committee will give you more beam time to rerun a new experiment. So resampling techniques are then used to generate new data in a cheap way. Techniques are used to generate new data. And this is actually something we have to put in quotation mark because we are not generating new data, but we are simply reshuffling the data we have and hoping that that gives a possibly better interpretation of the mean squared errors. So keep in mind now that what we are providing at the end is something like a mean squared error for the test data. We may provide a mean squared error of the observables we are looking at. We would like to provide a standard deviation. So what we want to is that these parameters which we present, they are parameters which we think have been treated in the best statistical possible way. So it's used to generate new data in order to obtain better estimates of statistical expectation values. And the mean squared error is one of them. Expectation value. Now let me just rewrite this one. And there are many such methods, and the simplest one to implement is actually the bootstrap method. So let's see what that is. So the bootstrap is one of these methods, and this is often used when you have little data. So suppose you have data in the hundreds to 1,000. So often small data set. So n ranges from 100 to 1,000. So the bootstrap method is extremely simple to implement. So what it means is that we have a data set D. So this is our original data set. So let me just call this x0, x1 to be simpler than what we did before. So this is our data set, which we have. Now, what we will do then, when we set up the algorithm for it, so the bootstrap method is widely used in statistical data analysis, and the standard method assumes that these are statistically independent and identically distributed events. I will show you a demonstration where we actually demonstrate the central limit theorem by doing bootstrapping. So I'm coming back to that a little bit later. So the algorithm here is one, reshuffle your data randomly, reshuffle D randomly, and pick data sets with replacement. So what does that mean? That means that we are going to produce a new data set, D1, which is going to be given by some x0 star, x1 star, x2 star, up to xn minus 1 star. So we have reshuffled the data set. And then we pick new variables, D1, with replacement. So as an example, suppose the original data set was just given by 1, 1, 2, 3, and 4. Then your D1 here could now simply be 2, 3, 1, and 1. So with replacement means that we put back the number which we have picked, and we can actually pick the same data set several times. Now, in the original paper by Efros, this was introduced as simple as it stands now, but later it has been shown that this is a method where you can, if you have independent and identically distributed variables, you can actually reproduce both the standard deviation and the mean squared error rather precisely, but you need larger data sets, obviously. But the thing is now that you produce a new data set, and when you have produced this data set, then you would calculate expectation values. So in this particular case, what you could do, for instance, is to calculate the mean squared error, which you call mu1. It could be the variance, which we call sigma 1, etc. Or it could be the mean squared error. Then we repeat this reshuffling, repeat 1, b times. So B now stands for the number of bootstraps. And there is no kind of golden rule for how big B should be. Some people put B equal to the number of data points. Some people take B to be 10% of the data points. But just keep in mind that this kind of reshuffling becomes time consuming when you have lots of data. So if you have 100,000 data points and you do 100,000 bootstraps just to generate 100,000 new data sets, then clearly that is going to take time. So the bootstrap method is often less favored compared to the cross-validation method, which actually requires in general less floating point operations. But the recipe here is now to repeat this operation many times, and then at the end, then calculate the final averages. Let's say mu, which is going to be given by 1 over b, and then we would have a sum from 1 equal 1 up to b, and then we are simply calculating all these averages which we made here. And we could calculate a mean squared error, which will then be given by the sum of all these bootstrap calculations which we have run, of beta, and then we have the mean squared error for each one of these cases here. So this is the simplest way we can think of the bootstrap method. It's extremely easy to implement. The only thing we do then is we reshuffle, pick new data with a replacement, and that defines a new data set. And then we use that data set to calculate the mean values, to calculate other expectation values. And then when we performed all these bootstraps, what we do then is that we simply calculate a general expectation value by summing up all the values which we had. So I wanted to show you an example here. And this is an example which I'm going to present in the on the whiteboard, no, on the slides. So I'm going to take an example of a Gaussian with n equal 10,000. So I have 10,000 data points. And I'm going to have a mean value. So I generate a Gaussian with a mean value of 100 and a standard deviation, sigma, which is equal to 15. So it has a pretty large standard deviation. So this is my original distribution, which I start with. And then I'm going to perform a bootstrap. And we know that if we use the central limit theorem, so then I'm going to perform, in this example, m bootstraps. And then I know that the standard deviation for this sigma of m here is going to be proportional with the original one divided by the square root of m. Okay, so this is nothing but what we call the central limit theorem. This follows from the central limit theorem. And we remember from the central limit theorem that mu with the original data set of n is going to be the same as mu with a new data set. So the only thing which will happen then is that we are going to get a standard deviation which is becoming smaller. So the bootstrap method is a method which is used often to demonstrate the central limit theorem numerically. And your error will clearly depend on the amount of data which you have. So what we are doing now with the bootstrap method, the implementation of it, instead of us generating new distributions here, let's say 10,000 times, so we have 10,000 data points, and one thing we could do is to generate new distributions 10,000 times. If I do that, I should actually get this. If I follow the central limit theorem, I should get this result here. That follows from the central limit theorem. So the central limit theorem states that if you have independent and identically distributed variables, so that means that the distribution is the same for all of them, and suppose you have 10,000 such variables, then if you repeat this many, many times, the new distribution will be a Gaussian, which has the mean value as before, and with a standard deviation, which is given by the original standard deviation divided by the square root of the number of trials which you have made, or the number of times you have produced new data. So you can look at this in two ways. One, you could actually take and generate new data, let's say 10,000 times. In addition to, so every time you produce 10,000, and then you just repeat this 10,000 times. Then your standard deviation should approach this number by the central limit theorem. Alternatively, you use the bootstrap method and simply use this data set, and you just reshuffle randomly and pick new data points with replacement, generate a new data that way, and then you calculate the expectation values. So the bootstrap method is a method which works extremely well with independent and identically distributed variables. And what you will see then is that this method here is one of the typical methods which is used to evaluate an expectation value like the standard deviation and the mean squared error. So let's go back to the whiteboard and take a look at the numerical implementation of the bootstrap method. So let's just bring it up. So there is an example in the lecture notes. So I'm just going to skip these methods. There is a reminder of the central limit theorem. So just take a look at it. And if we now look at this specific example, which we have here. So what I'm doing is now to generate this distribution with 100 as a mean value. It has a standard deviation of 15, and I generate 10,000 points. And I simply do a random normal distribution here. And this is now generating a Gaussian with a mean value of 100 and a sigma of 15. And then what I do next is that I use this simple function in Python, randint, which now reshuffles my data. And then I pick a new data from that one by replacement. So this is done in this function randint here, and it runs over the whole data set. And I then calculate standard deviations and mean value by doing this 10,000 times. So my number of bootstraps is going to be given by the number of data points. So you could think of this as another way of generating this distribution here 10,000 times with 10,000 points. So if I run it now, and what I'm going to get is something which should agree with the central limit theorem. And you see now this is also something which takes time because I'm doing this 10,000 times. You see now that my original mean squared error, and since I only have 10,000 data points, I don't get 100. Keep that in mind. So I put in 100 here, but since I don't have a large, if I were to move this to 100,000 or 1,000,000, I would get closer to 100. I don't get the exact sigma either, or standard deviation. Now my mean value is basically preserved, and now I get a standard deviation, which is 15 divided by the square root of 10,000, which is 100. So that's a 0.15. And if I plot it, what happens now is that my mean value is centered around 100, not exactly 100, but 99.8. And you see now that if I look at one standard deviation, this is between 0. So I have a 997, as it said here, 77, plus minus 0.15. So what the bootstrap method is doing for us, it is producing a distribution of the mean values. So what I'm simply doing here is actually look at the distribution of mean values. I'm simply counting the number of times I get 99.5, 99.6. I have made bins with size 50 here. That's the way I actually make 50 bins in the domain from 99 up to 100.5. So that's the domain I'm using now to make this plot. And it simply counts the number of times I've observed that specific mean value. And you see that this is centered around 100, roughly. It's not exactly 100. If I were to change this to 100,000, it would take me much more time. But I would get something which is closer to 100. So all the results, this is also kind of warning that all the results I'm setting up will depend on the number of data points which I have. But what you see here is a demonstration that the bootstrap method gives you what you expect from the central limit theorem. And the bootstrap now is a method where you can now say that, okay, instead of using 100 data, 10,000 data points, I could simply reduce this to 100 times. I don't need to do as many bootstraps as I have data points. So this is again something which people can play around with. Any questions so far? Okay, so this was using the bootstrap method, which is just you reshuffling the data randomly and just picking with a replacement and then computing an expectation value and then just repeating this exercise again and again and again. And then what you end up with is a demonstration of the central limit theorem. So what I'm going to do now is to look at the next topic before we move on to cross-validation, which is another one of these methods. We are going to take a quick look at the bias-variance trade-off. And if we now start with a mean value, this is a quantity which we now have defined as an expectation value. We can rewrite this quantity by some manipulations, which I'm going to show a little bit later. We can rewrite this quantity in terms of the variance of the model itself. And we can rewrite this as a deviation from the data which we want and the mean value of the model, plus this variance sigma squared. So what is this going to mean? Let me just try to give an interpretation of this bias-variance trade-off in terms of a simple image. So what we've done now is simply to rewrite the expectation value of the mean squared error in terms of three terms. One, this sigma squared from the noise, and then we have the variance of the model itself, and then we have the deviation of the model, the mean squared value of the model, from the data points which we want to reproduce. And there is a simple way to look at this. So let's switch over to the whiteboard and take a closer look at a simple example. Because as I mentioned, this bias-variance trade-off is a way to analyze when the test expectation value starts showing deviations from the the train expectation value and leading us into a region in terms of overfitting. And the best way to do this is actually to look at the mean squared error. So what we have is actually a mean squared error, which we normally rewrite in terms of a bias, plus a variance of the model itself. So this is how much the model varies, and we have this y tilde, or the model varies internally. And the bias is going to be given by an expectation value of 1 over n. And the only thing we do now is just to rewrite the mean squared error. So I'm going to have a y of I minus the expectation value of the model. So this is something which we just calculated, just a constant, plus the variance here. This is the variance of the model itself. And let's try to understand this from a simple image. This is yi tilde minus e. And next week, we are going to derive this expression. So this is the variance of model itself. So one way to understand this is to look at a simple image. And this is roughly where we will end today. And we will try to wrap up this discussion during the first lecture next week. So let's now look at a simple example. So suppose the target is this one. This is our target. And then we have these circles like this. And suppose now that we have a model which has a bias which is high and a variance in the model which is low. So the red is the target, so we want that specific point. Now, if we have a small variance in the model, the predictions which we are making would be centered. So the cross here is the mean value of the model. And then the predictions we make would be clustered around this model. So we would then say that when we look at this, so this is the E, the mean value of the model. And when we have a low variance, it means that the predictions we make are clustered around that mean value. However, this mean value of the model here, so this is a tilde, it's not a square. You see now that you have a large deviation here. So we have a large deviation, which gives from Y, and our data is this one, and that leads to a large bias. Because if you go back to the expression, what we have now is a mean value, which is far away from the points we want to predict. In our case, there's just one point we want to predict here, right? So this is that point which you see here. This would be an example of what we call a high bias and a low variance. Then what we could have is the next case where we now repeat. This is what we want, and then we have these circles. What we could have now is a case with a low bias and high variance. So in that specific case, we could have a mean value, which is here, but then the predictions we make are scattered all over. So we have a high spread, so the variance just measures the spread in the model. Now, when we have a large spread in the model, this is a typical case of overfitting, because the predictions we make are widely scattered. So the bias-variance trade-off is used as a way to study the occurrence of overfitting within a specific model complexity. Then what we could have is a case where we have a high bias and high variance. So let's just redraw this. So we would have high bias and high variance. That's also a case which is unwanted and which is a typical example of overfitting again. So we would have a mean squared error, a mean value for the model, which is far away. And then we would make predictions which are scattered all over. Now, the ideal, which we want to have, is a low bias and low variance. So the model we are searching for is a model which is actually looking something like this. So we would have the circles here, and then we have a very low bias, so we are pretty close here. And then the predictions we make with the model are very close to the mean value of the model. So this is the ideal. So this is a case of overfitting when we have a high variance in the model. This is also a case of overfitting, whereas when we have a bias, a bias which is high and a variance which is low, this can often be a case of underfitting. But in general, we are more interested in the case with overfitting, because what we want is a situation where we have a training mean squared error, which is pretty close to the test mean squared error. But when they start to deviate, that's a typical case where we have trained a model to perfection, but then this model which we make is so much tailored to the specific training data that when we apply it to data which was not included in the training, we do actually fail. And that is seen in a situation where we have a high variance, like in the case which we have here. In this specific case here, this is a high variance because we actually having a model which has a huge spread in predictions. When you have something like this, then you know that some fine-tuning can bring this mean value closer to that one. This is just like you being in a shooting range and you are trying to aim better. And in the beginning, you have all your hits in here. And then you know that you just need to adjust your aim a little bit in order to get closer to the target. And with the overfitting, that is a situation where we have basically a model which does very poorly. And the ideal is something like the one which you see here. So next week, we are going to derive this relation which you see here, this one, which is just a way to analyze the data. And then we are going to apply this to a simple model, which you will find in the slides here. And then we are going to present at the end of the first lecture next week, the cross-validation algorithm, which is the one which is used routinely with essentially all machine learning methods in order to produce what we think is a more reliable estimate of, let's say, the mean squared error or other ways to gauge the quality of the model. Okay, so we didn't finish what we planned. So let me just bring back the whiteboard here. Not the whiteboard, but the slides. So what we are going to do next week in the first lecture is to go through an example code for the bias-variance trade-off. And then after that, we are going to take a look at the steps in cross-validation, which is a standard method for trying to estimate the best possible, let's say, mean squared errors or whatever. Because when you present the data, you always evaluate things like a function like the mean squared error, the R2 score, or other ones, which give you a kind of a measure of the quality of your model. Or if you're dealing with a classification problem, it could be the number of correctly classified events, etc., etc. And these are quantities which we want to be as reliable as possible. And that's where these resampling techniques come in, as a cheap way to generate more data. That's the overarching idea behind the resampling techniques, since we are always limited by a data set. And the less data we have, obviously, the larger scatter we will have in a specific expectation value.